Welcome back to a new chapter in geometry. What we're going to be beginning today is talking about triangle congruence. But to begin with, what I want to do is just reiterate some of the topics covered at the end of last chapter, which is the law of sines and law of cosines. I have written those down for you right here for you to be able to reference if you need some help with the the law of sines and the law of cosines. But going back to what we did in the last chapter, see if you can solve for the missing variable x in both of the diagrams using the law of sines and cosines appropriately. As a reminder, the big letters represent angles, and the small letters rather, represent side lengths. So in this specific problem right here, if you wanted to call this thing angle A, the side length across from that would have to be little a, and so forth. So I'll give you a moment, see if you can't solve for those, and then we'll come back and we'll talk about it. Alright, let's check and see how we did. On the first one, I set up my law of sines, as I did over here, and in this case we were solving for angle B. I did not know what that was, so I set up this ratio using the law of sines, and in order to do so, I cross-multiplied. And so when I did that, I got 13 times the sine of 52 equals 15 times the sine of B. Then if I wanted to solve for B, what I need to do first is divide both sides by 15 to get the sine of B by itself. Now in this case, I don't want the sine of B. What I want is just angle B all by itself. So in order to undo the sine, what I need to do is the inverse sine of both sides. That gets rid of it. So when I typed the inverse sine of this thing right here, 13 times the sine of 52 divided by 15, that's going to give me a decimal. And I typed the inverse sine of this answer into my calculator, and that got me 43.07. So the measure of angle B is 43.07 degrees. Now in the last problem, the one down below, dealing with the law of cosines. In this instance, I called the side length across from my angle little c, and that was big C. So this would be set up as the following problem, trying to solve for that side length x. And so as you go through, remember that when you solve for this thing, these two things need to be multiplied before you solve for anything else. 108 times the cosine of 93. And then make sure that you pay attention to the fact that you're subtracting a negative, which really makes a positive. So it's like you're adding together those two quantities. And so you end up getting 122.65, but remember you need to take the square root of both sides, as that's x squared. And so when you take the square root of both sides, that gives you x equals 11.07. Alright, what we're going to do today is we're going to move beyond similar triangles, and what we're going to do is we're going to talk about congruent triangles. So it says in Chapter 3 you learned how to identify similar triangles and use them to solve problems. Well, what about when triangles are congruent? So to begin with that, what we're going to do is we're going to look at this problem 6-1 that says examine the triangles at the right, and it says make a flowchart showing that these triangles are similar to one another. So as a reminder, we have three similarity conditions. We have angle, angle, side, 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 and side, angle, side. And in this particular instance, it looks like we're going to be using side, 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 as we have three sets of sides in both triangles. So to create a flowchart for that, remember what we're going to do is we're going to create three ovals, and within these three ovals are going to be our three sets of sides that we are saying are proportional to one another. So for me, that would say like side length AB is going to be, well, I need to make that a little bit smaller. Side length AB is going to correspond to side length FD, and that ratio is going to be 6/6. Side length AC is going to correspond to side length FE, and that ratio is 7.5 divided by 7.5. And then lastly, we can say that side length BC corresponds to DE. So BC corresponds to DE, and that ratio is 4.5/4.5. And so what you should recognize within each of these is that we have a constant ratio, as all of these are equal to 1. And so we therefore have the same proportionality between all three sets of sides. So what we can conclude then is that triangle ABC is going to be similar to triangle FDE, and our reasoning for that was by side, side, side similarity. So it says, are these triangles congruent in part B? And the answer would be yes. I know they are congruent because the scale factor between all of the sides is 1. The ratio of all of the sides, all of the corresponding sides, is 1. So not only are they similar triangles, but they are congruent. So not only do they have the same shape, but the exact same size as well. So here's a big deal in letter C. It says, while the symbol for similar figures is the tilde, the symbol for congruent figures is an equal sign with the tilde on top. So how is congruence related to similarity? Well, congruent, that's what this means for two shapes to be congruent, is the same shape and size. And so essentially, how does that relate then to similarity? Essentially, they are figures that are similar with a scale factor of 1. So if you have two shapes that are similar, as we showed up here up above, they have a scale factor of 1 with one another. Okay, so on letter D, to kind of recap this idea, we can say that triangle CAB, if we just reordered our letters, is actually now congruent. So if I went CAB, I would have to go EFD with my other vertices. So it would look like this, EFD with CAB. Cool. What I wanted to do in problem number 2 is just look at a couple brief examples of triangles that could be congruent to one another. What I want to do is actually begin with part B. Notice that this side length right here and this side length are the exact same measure, as they both have 2 tick marks. Notice also that we have the same angle shared between both the triangles. And then remember, if two triangles share a side length, that's going to be the exact same in both triangles. So these two triangles actually are similar, but now we can say they're actually more congruent. We can say that triangle ABC is going to be congruent to triangle DCB by side angle side. And the reason I know it's side angle side is I have this triangle right here with 2 sets of sides and the angle in between it being congruent to this triangle down on the bottom with 2 sets of sides and the angle in between that as well. And so I know that the scale factor between those sides is 1, and the reason I know that, even without any measurements, is because these tick marks right here, these tick marks match up here, and this side length is shared by both triangles, so therefore they are congruent, not just similar, because the scale factor, we use the letter K to denote scale factor, is 1 between all of the sides. Down here on this, actually I don't want to skip that one. I'm going to skip that one. Just get an idea of how we can recognize triangles being congruent rather than similar. We'll go on to problem number 3 and finish up there. Problem number 3 here, again, talks about a square with diagonals intersecting at R. It says how many triangles are in this diagram. Well, you can spend some time looking at that. There are actually 8 triangles within this diagram. You can see these 4 right here, but then there are also some larger triangles as such, and you could repeat that exact same process going all the way around for many of the different triangles within that picture. But it says how many lines of symmetry does this thing have? Well, it has 4 lines of symmetry, and it says write as many congruent statements as you can that involve congruent triangles. Well, one set of congruent triangles, I know that since there are lines of symmetry here, I know that this side length is going to be the same as this one, which is going to be the same as this one, which is going to be the same as this one. So I know for sure I can say triangle MRQ is going to be congruent. So MRQ is this triangle right here. That's going to be congruent to all of the other smaller triangles there. So for example, triangle MRN by side, side, side. And I can do the exact same process for the other 2 smaller triangles there, and I could repeat it for the larger triangles as well. But again, just getting into the idea that triangles can be more than just similar, but they can also be congruent if they have a scale factor of 1, which is what the next slide is going to hit on. It says this: the information from chapter 3 is reprinted for your convenience. It says 2 figures are congruent if there's a sequence of rigid transformations that carries one onto the other. So essentially they're saying, hey, if you can just rotate, flip, or translate this triangle onto the other one and see an exact fit, we call those congruent. So they are similar and have a common ratio or a scale factor of 1. So in this particular instance, you can see that the side length of 9 matches up. We have a side length 5 that matches up, and we also have a side length of 10 that matches up. So the correspondence between all of the corresponding sides has a ratio of 1. 10 divided by 10, 9 divided by 9, and 5 divided by 5 is all 1. And then all of the corresponding angles are also equal to each other. So everything in those triangles, all the corresponding parts are the exact same. So congruence, at the end of the day, means the exact same, building on our idea of similarity. We're going to build on that more tomorrow. If you have any questions, please feel free to swing by office hours, and we will talk soon. Stay safe and stay healthy.